Welcome to Engineers Academy. Subscribe to my channel and click on the bell icon to receive the notification for the upcoming videos. So now in this lesson we are going to solve this problem. In this problem we need to construct a tank which consists of two parts. One part is the cylindrical part and the other part is the hemispherical top. So then in this problem it is said that the tank is to be constructed to hold a total volume of 5 cubic meters. So the total volume that needs to be filled is 500 cubic meter. And the surface area of cylindrical part is 2 pi RH. So the surface area of cylinder is 2 pi RH. And its volume is the volume of the cylinder, as we all know, is pi r square h. And the surface area for the hemispherical part is 2 pi r square, and the volume for the hemispherical part is 2 pi r cube divided by 3. So now I will write two equations. So one equation is for volume, so I will write the total volume equation. So the total volume will be the volume of the cylinder plus volume of the hemisphere, and it is equal to 500. So volume of the cylinder is pi r square h, and the volume of the hemisphere is 2 pi r3 divided by 3 and equal to 500. So now if we write h, the equation for h in terms of r, so I will write 500 minus 2 pi r cube divided by 3, and this whole divided by pi r square. So I can write it like this: 500 divided by pi r square minus, and then I will write 2r divided by 3. Pi and r square cancel out, so one r is left. So we have this equation for r, and now I will write an equation for cost. So for cost, it is stated that the cost to construct the cylindrical part of tank is 300 per square meter. So the cost for the cylindrical part is 300, and the surface area of the cylindrical part is 2 pi r h, and the cost for the hemispherical part to construct is 400. So I will write 400 into the surface area of hemisphere, so it is 2 pi r square. So we have these two equations. So now in MATLAB what I will do is, first I will define a radius row vector, and I will write the range is given for. The range is here, given here that the r is from 2 to 10. So I will write r, and I will give some spacing. So we will define r like this in MATLAB, and then we will find the height for each corresponding radius. And then once we find the height for each corresponding radius, so then we will use this equation to find the cost for each radius and height. And keep in mind that h is a function of r, only a function of r. So whatever is the dimension or order of this r row vector, height will have that same length. Let's suppose if we find the length of r in MATLAB, so it will be equal to the length of height. And similarly, cost is a function of both r and h, so the length of cost will also be equal to the length of cost is also equal to the length of r and length of height. So keep in mind. So then we can say that, let's suppose the first element of r will be, let's suppose 2. So the first element of h will be the height for this corresponding r value, and similarly the first element of cost will be the corresponding cost for this radius and height. So keep in mind. So let's suppose if the 10th element, if the radius of 10, that is the 10th element of radius, is some value, let's suppose it's a capital R value. So for that 10th value, the corresponding height will be h10, the 10th element in the row vector of h. So that will be the corresponding h for this r. And similarly, if we want to find the cost for these two corresponding radius, so the cost of 10, so the 10th element in the cost row vector will also be the corresponding cost for these two. So now let's write this in the MATLAB. So how to do it in MATLAB? I have already written these three equations. One is for the r. So we have defined the radius, that is from 2 to 10. And I have wrote the same equation, that is 500 divided by pi into r square. And keep in mind that r is a vector. So then if we want to take the square of this r, so then we need to perform an element by element operation. So we need to put dot here as well, and then we need to write minus 2 into r divided by 3. So it's that same equation. Then I wrote the cost equation that I have evaluated in the here. This is the same cost equation. So now in the problem, if I run this, let's suppose, so here we see that for r is equal to 2, the first height is 38.4554, and for r is equal to 2.1, the next r will be 2.1. So for 2.1 radius, the height is 34.6896, and for radius equal to 2.2, this is the corresponding height. And similarly, for the first height and radius, the corresponding cost is 1.5503 into 10 raised to power 5. And similarly, for the second radius and height, the cost is 1.4840 into 10 raised to power 5. So now we need to find the minimum cost as well. So let me suppress these. I do not want to print them on my command screen. So then I will write, I need to find the minimum cost. So I will write minimum cost, and then I want to find the location of minimum cost in the cost array. So I will write the address, and then I will write minimum of cost. So we know the minimum function, right? So I will use this equation. So now if I run this, so now it says that the minimum cost is 9.1396 into 10 raised to power 4, and the address of this minimum cost in the cost array is 30th element. So now if I run this, so what we see that the minimum cost is 9.1396 into 10 raised to power 4, and the address of this minimum cost is 30th. Let me change the formatting. So if I write format short g and I run this again, so the minimum cost is 91396 and the address is 30. And now if I check this 91396 cost in the cost array, so it will be the 30th element. So if I write cost, so the 30th element, 2930, so this is the 30th element, 91396. So keep in mind that minimum always gives us the address of that minimum value as well. So we have learned this, right? So now we know the minimum cost and the address of that minimum cost. So now if I want to find the corresponding radius, so we will write r and the address. So the 30th element in the r row vector will be that corresponding r value. So let me store this in capital R. And now if we want to find the corresponding h, so I will write h and I will write the 30th element in the h row vector. So now if I run this, so the minimum cost is 913966, the address is 30, the corresponding radius for the minimum cost is 4.9 meters, and the corresponding height for this minimum cost is 3.362. And in the problem it is also said that also plot the graph between the cost versus radius. So I will write radius and then I will write cost, and then I will write x label, and the x label is what? The x label is radius. And then I will write y label, and y label is, the y label is cost, so I will write cost. And then I will also write grid on. So now if I run this, so we see that there is a minimum value, and if we check, this is a cost versus radius graph, so we can see that at radius 4.9 the cost is minimum. So now let's print another graph between h and cost. So let me edit this. So if I want to have a graph between h and cost, so I will change it here as well. So I will write height. So if I run this, so here we can see that at somewhere 3.3 the cost is minimum as well. So in this way we can find the corresponding radius and height for the least cost. So now if we use this 4.9 radius and the height of 3.362 meters, so we will have this minimum cost, and the volume occupied will be 500 cubic meter. So I think you people will have understood this problem. So now let's solve this problem. So this is another problem from chapter number 2. So in this diagram we can see that here is a beam and a cable, and a weight is supported to this beam, and the tension, there is some tension in this cable. So it says that a cable of length LC supports a beam of length LB, and so that it's horizontal when the weight is attached at the beam. So it remains horizontal when the weight is attached to the beam, and the principle of statics can be used to show that the tension force T in the cable is given by this. So the equation for the tension is derived by using the equilibrium conditions. So where D is the distance of the cable attachment point to the beam point, which is shown in this figure. So what we need to find, so for the case where W is 400, when the hanging weight is 400 and the length of the beam is 3 meter and the length of the cable is 5 meter, so the problem says that use element by element operations and the minimum function to compute the value of D. So we need to compute the value of D that minimize the tension T. So compute the minimum tension value. So we need to find the D value, the distance of this point from this hinge point at which the tension in the string will be minimum. The tension in the cable need to be minimum for that D. So how to do this? So it's very simple. What we will do in MATLAB is I have wrote W is equal to 400, the length of the beam is 3 meter and the length of cable is 5 meter, it's given, and D. So D is from 0 to length of beam. As we can see that D cannot be out of the beam. So the maximum limits for the D is 0 to LB. And the tension in the cable is given by this equation. So I have wrote LB. LB is constant multiplied by LC, which is constant, multiplied by W weight, which is constant. So then I need to divide this by, this is given, so D into square root of LB, which is constant, to the power 2 minus D. So here I have wrote dot. So D is a vector. So then when it's a vector, so then we need to write element by element exponentation. So this is that equation. If we run this and I display T, now we see that this T is a function of D. All other variables are constant. So now with each corresponding D value, when D is 0, the tension in the cable is infinity. And then when D is 0.1, so the tension is 2.0011 into 10 raised to the power 4. So now we have these tension values. So now in the problem says that we need to find the D minimum value for the T minimum. So the optimum value for the D when the tension is minimum. So I need to find the T minimum. So I will write T tension minimum and then I will write, let's suppose, the index, and then I will write minimum, and then I will write t. So now if I run this, and then we see that the t minimum is 1.336 into 10 raised to the power 3. So if you people do not want to see it like this, so you people can change the formatting. Again, I have told you people, so I will write format short g, and if I run this again, so the t minimum is 133.6 and the index is 22, and these are all the corresponding tensions in the cable. So the index is at index number 2, the t minimum is there. So let's check it. So the 22, so this is the 22nd element of all the t minimums for each corresponding d values. So now we know the t minimum value, so now we need to find the d optimum. So I will write d optimum, and d optimum is equal to d vector and the 22nd element in that d vector. So now if I run, so the d optimum is 2.1 meter from the hinge point. So if we tie the cable at a distance of 2.1 from the hinge, so the tension in the cable will be minimum. Now in the second part, it is said that check the sensitivity of the solution by plotting t versus d, and how much can d vary from its optimal value before the tension t increases 10%. So it says that if we increase the minimum t value by 10%, so what will be the value of d? So let's find that. So if I write the t increase, and I will write t minimum plus 10%, I will add 10%, so I will write 0.1 into t minimum. So now if I run this script file, so what will be the result? So if I run this, so then we see that the t minimum is 1.336 into 10 raised to the power 3, and then the index is 22, and the d optimum is 2.1000, and if we increase the tension, the t minimum, by 10%, so the new tension, the increased tension is 1.467 into 10 raised to the power 3. So now in the second part, we are asked to find the d value for this 10% increase in the tension. So we cannot find it directly, so then what we will do, we will use the graph of the t versus d. So let me plot the graph. So I will write plot, then I will write d versus t, and then I will write labels as well. So I will write x label, so x label is d, and y label is tension, and let me grid on as well, grid on. So let me run this. So now we see that this is the graph. So at d is equal to 0, the tension is infinity, and as the d increases, the distance from the hinge point of the cable increases, so the tension decreases, until we see that from 0 to 0.5 the decrease is abrupt, and then there is a gradual increase from 0.5 to 2.5, and as the d distance reaches the end of the beam, so then the tension again reaches the infinity. So now we need to find that new d value for 10% increase. So we cannot find it from here. Here we can see that the 10% increase, the tension is 1.46 into 10 raised to the power 3, and here the tensions are given in the form of 10 raised to the power 4. So then this is 0.1467 into 10 raised to the power 4. 0.1467 is somewhere here. so we cannot extract it from this graph as well. So how to extract it? So let's search this value in the t vector. So if I write t, so this is again t is in terms of 10 raised to the power 4, so it's 0.1467 into 10 raised to the power 4. So we will search 0.1467, so I see that 0.1467, 0.14 and 0.15, so somewhere here between 0.1447 and 0.1542, so somewhere here. So we can take the average of these two values to just compare that. So it's the 26th value, 26th and 27th value. So now if I check the D26th element, so D26 is 2.5. Let me write it here. So I write D26 and also I write D27. So if I run this again, then we can see that for 10% increase in the tension, the D value will be between 2.5 and 2.6 somewhere. So we can take the average of this. So as we can see that what is the D optimum value, if I find the difference, if I write difference is equal to, let's suppose I write D optimum minus, and I write, let's suppose, D26. So D optimum is that the distance for which the tension was minimum, and D26 is the D value for which the tension is increased by 10%. So let's see the difference. So now we see that the difference is minus 0.4. This means that the D26 is 0.4 more than the D optimum value. How much is the tension increase? Let's find the tension increase as well. So I will write tension increase value. So let's find the tension increase value as well. So I will write tension increase, and this will be tension increase value, let's suppose. So I will write this, and I will write tension increase is equal to tension increase minus T minimum. So now again if I run, so we see that when for 0.4 increase in the D, 0.4 meter increase in the D, so the tension increases by 133. So this case is very sensitive. This means that we cannot increase D as a lot from its optimum value. So when we increase the tension by 10%, so the increase in D is 0.4. I think these two problems are enough for today. I hope you people will find this very helpful for learning in MATLAB. Kindly let me know if you people have some problem. Kindly let me know by writing your comments. And if you like my videos, click on the like button as well.